So we mentioned Compton earlier. Compton looked at the Compton effect, the thing that's now known as the Compton effect, which is the scattering of photons and electrons. And what we mean by scattering is we literally mean collisions between photons and electrons. And what Compton was able to show is that you can explain what happens when you collide a photon with an electron if you treat the photon as a photon, right? We're already talking about like it's a particle. He showed that light acts like a particle in a collision with an electron. So, and I'll probably say more about this later, but just to, one of the things that's important to understand about this effect is that it couldn't be determined until X-rays were discovered because of the high energy nature of the photons. And with lower energy photons, the effect was lost in the noise of the experiment, and you needed high energy photons in order to discern the effect that the photons act like a particle. Hopefully that'll become clear later, but it doesn't matter. It's important to know that this experiment could only effectively be done with X-rays because they're high energy photons, and the high energy meant that the effect was not lost in the noise that is present in experimental physics. So remember, what is a photon? A photon is a packet of energy. It is a wave packet. It's what's called a wave packet. So you can think of it as a wave that takes up only a finite amount of space, or a particle. That's what a wave packet is. And the energy of the photon is equal to hf. But that also means that perhaps the photon has momentum, and this is what's added with the Compton effect. Einstein did also say that the photon must have, if it has energy and if it's treated like a particle, then it must also have momentum. Oh my gosh, light having momentum, but it's a massless particle. Einstein never said photons have mass, right? They do not have mass. We know photons are massless particles, or they're massless, but they do carry momentum. The easiest way to show this is to go back to relativity and remind you that one of the very last things we said when we were talking about the momentum and energy of relativistic particles is the relationship between energy and momentum is this. And we simply look at the fact that if it's massless, then this quantity goes to zero, and so therefore E squared equals P squared C squared. I didn't mean to change colors. Therefore, P equals E over C for a massless particle. Important from now on. That's what Einstein was able, or it was important before too, but we haven't said it before. Einstein was able to say that a massless particle should have a momentum. If it's got an energy, it's got a momentum, and the momentum is simply E over C. And what Compton was able to show is that indeed, when you collide a photon with an electron, that it acts like a particle with a momentum, E over C. Pretty cool. Notice that also means that therefore for a massless particle or for a photon, E equals HF, P equals E over C, which is HF over C, which is, F over C is, right, because F lambda equals C, F over C is just lambda. So it's F over C is 1 over lambda, H over lambda. I feel like we saw that somewhere before, and I said we would show where it came from. Maybe we didn't. But the momentum of a photon is also just H over lambda. It's all of these things. Let's see what the Compton effect is. So let's just take a stationary electron. Take a stationary electron. Let's make our electron purple. And let's collide it with, and let's just treat it like a particle. Let's call this a photon. And that photon has a certain amount of energy, so it's got a certain amount of it's got a certain frequency, F0, because remember, energy is proportional to frequency. I mean, the proportionality constant is just the Planck constant. So talking about the frequency or the energy is really talking about the same thing. When we're talking about the frequency or the energy, we're talking about the same thing. So this is first year physics stuff, right? If we're going to collide two particles and we see what comes out, right, after the collision, and let's do this in 2 dimensions rather than 1 dimension, then let's say, one glances off the other. Think of this like 2 billiard balls. Let's make the electron go off in this direction at some angle relative to the initial some angle. Let me look up what angles I used in my notes. So the photon goes off at some angle theta, and the electron goes off at some angle phi. And by the way, the I guess that was meant to be a photon on F. Hold on. I was getting ahead of myself there because the energy of the photon has to change. So it's got an initial energy or frequency of F0, and it's got a final energy which is different, right? We'll just call it F. But anyway, we'll get there. So let's go ahead and do the the dynamics of this collision, just like first year physics. We're going to conserve energy and momentum in order to see what we think should come out. So let's say that we know we've got stationary electrons, we know that we've got a light of a certain color, and we collide the light with the electrons, and then we measure the energy of the electrons that come out and the energy of and the color of the light that comes out, the energy of the light that comes out. And if we can treat the light like a particle, then energy and momentum should be conserved like a billiard ball collision. So that's what we're looking at, is that we're just looking at the energy in and the energy out, the momentum in, the momentum out, and seeing if this acts like a billiard ball collision. So it's going to be energy of the photon initial plus energy of the electron initial equals energy of the photon after the collision plus energy of the electron after the collision, right? Before the collision unprimed, after the collision primed. So this isn't a relativistic prime unprimed thing. This is just before and after. We could do initial and final instead. And we're going to do the momentum of the photon plus the momentum of the electron before the collision equals the momentum of the photon after the collision plus the momentum of the electron after the collision. Just going to plug in, right? Energy of a photon is HF, energy of the electron is, and we'll make it relativistic because that's no loss of generality, right? Relativistic, we can always, the relativity might end up being the same as non-relativistic. But anyway, so for the electron, we're going to have an initial energy, which is just its rest energy because it's at rest, of mc squared. What else? And for the sake of the math, because this is going to start getting messy, I'm not going to plug in anything for the momentum to begin with. Let's just see. Let's start plugging in some things. So for the energy equation, what we're going to end up getting is HF initial plus the initial energy of the electron, mc squared. So that's the mass of the electron. We should know that. Equals HF final. I would call that F prime. The new frequency, if it changes energy, it's going to change frequency. Plus, let's just for now say the energy of the electron after the collision. I should have written down the energy momentum relationship from relativity because we're going to need to use that later. So when I said E0 equals mc squared, E in general can be written as E squared equals mc squared, m squared c to the fourth plus p squared c squared. That was Einstein's relationship between energy and momentum. And if the momentum is 0, right, then we're at the rest mass equals mc squared. Okay, anyway, we're going to need that later. Okay, coming back to this. Now from the momentum, before we plug anything in for the momentum, let's just realize that how do we conserve momentum? We need to look at the x direction and the y direction. The x direction, we'll call that the x direction plus x, and that the y direction plus y. So in the x direction, we've got the momentum of the photon, and the electron has no momentum. The momentum of the photon plus 0 is equal to, afterwards, in the x direction, we've got the momentum of the photon after the collision times the cosine of theta plus the momentum of the electron after the collision times the cosine of phi. So that's a momentum conservation in the x direction. In the y direction, momentum conservation in the y direction. Before, there's no momentum in the y direction, 0, because nothing is moving in the y direction. After the collision, we've got p of the photon after the collision times the sine of theta plus p of the electron after the collision times the sine of phi. You caught my error that the photon is going in the negative direction and the electron is going in the positive direction. So there was a minus sign right here that I had left out. Compton experiment, what we're actually going to be looking at when we do this experiment, which I haven't really described in detail yet, is we're going to be looking at the photons that come out. So we are interested in the angles of the photons that come out. And so what we want to do is we want to get rid of, we don't care about the angle phi, we only care about the angle theta. So we want to get rid of phi, so we're going to solve together the two momentum equations to get rid of phi. Our two momentum equations, and how can we get rid of phi? Well, let's square both equations and add them, right? Because if we square both equations and add them, we should solve for this, and then square both and add, so that the cosine phi, sine phi turn into 1. Simply solve the first equation for p cosine phi and solve the second equation for p sine phi. Now I've squared both equations. Now I've added the two equations, add the first equation to the second equation. I get the last equation, because cosine squared plus sine squared is 1. Remember, our energy equation was this, and I'm going to go ahead and make a substitution for the energy with the relativistic energy, putting it in terms of momentum, because we now have an expression for PE prime squared at the bottom here that we can plug in. So we literally just take the expression from the previous page, we plug it in here for PE prime squared, we plug in the expression for the energy into the energy equation, and we solve. And we do make the substitution F equals C lambda. I'm not going to do these steps because I have a full page of algebra, but it is truly just solving. It's algebra. There's no calculus, no complicatedness. It's just messy algebra. And what we end up getting is that instead of doing frequencies, it's easier to write it in terms of wavelengths. Something that's actually a pretty simple equation, that the wavelength of the light after the collision minus wavelength of the light before the collision is going to be equal to some constant, h over mc, times 1 minus the cosine of the angle. What angle? What angle is that? That's the angle of the detected light from the original path of the photon. So we usually write this as delta lambda, the change in wavelength of the light. And remember that this m here is the mass of an electron, because nothing else has mass here, but that's the mass of the electron. And this quantity h over mc, because it's kind of like a wavelength, or it is actually a wavelength, it's a wavelength of something, h over mc is called the Compton wavelength. Obviously you can go ahead and plug numbers in for that and find that it's 0.00243 nanometers. Again, we often talk about wavelengths of electromagnetic radiation in terms of nanometers. So what's going on here? What's going on here, remember, is that we've got photons coming in along the x-axis, and those photons are scattering off of electrons. And we can measure the photon, whoops, that was supposed to be a photon. We can measure the photon at some angle from the axis. And the change in wavelength of that photon, right? If its original photon had wavelength lambda 0, and this final photon had wavelength lambda prime, then the change in wavelength should be dependent on the angle, right? It's equal to some constant, the Compton wavelength, whoops. The change in wavelength after that collision should equal some constant times 1 minus cosine theta. So what Compton did is he did an experiment where he shot photons at electron targets, and he measured the wavelength of the light around this apparatus. So he had some device which he could rotate around the apparatus, and he measured the wavelength around the apparatus, and he found when he detected photons at different angles that they had this relationship, when he detected photons, he was able to measure their wavelength, and he found that their wavelength changed as a function of angle. And he found that it changed indeed, like this equation shows, which means that photons can be treated like particles. Because in order to get this result, we had to treat the photon like a particle. So this proved that photons had energy hf and momentum h over whatever it is. Momentum h over lambda. Energy hf, momentum h over lambda. That was the assumption to begin with. And if he does this experiment and finds that indeed that the change in wavelength of the photons as a function of angle is this, then they've got those properties. And they did. This is a little qualitatively and quantitatively. First of all, if theta is 0, in other words, if the photons are not scattered at all, if theta is 0 and they go then they go straight through without being scattered. And with theta equals 0, then cosine of 0 is 1, and the change in wavelength is 0, right? So if they go straight through and they're not scattered, that means that they haven't deflected off an electron, and their change in wavelength is 0. By the way, the reason why there is going to be photons at different wavelengths is because he's scattering photons off of a target which is made up of a lot of electrons, and some of the photons come closer to electrons than others, right? So they're all going to have the photons that come out. It's not a single photon scattering. This is many photons, and the photons are all going to come out with different energy because they are in different vicinity of the electrons in the scattering target, right? This thing is called the target. You just basically have whatever, some material that you're shooting your photons at. And then you just have a detector. It's literally a detector on a dolly that can go in a circle around the target and measure the photons that are coming out at different angles. Okay, we had already said that. What about photons that are scattered at, 90 degrees? Photons that are scattered at 90 degrees. Are photons going to be scattered at 90 degrees? I'm not entirely sure. Is that even possible? I don't think that is, because all the momentum would be gone in the x direction. But photons can be scattered backwards. And what about 180 degrees? What about the photons that are scattered at 180 degrees? They're the ones that are scattered right on, dead on an electron. If they're scattered dead on an electron, then the photon's going to come back, right? And so you're going to have theta is 180 degrees, and so that means delta lambda is equal to h over mc times 1 minus a minus 1, or 2h over mc. Equals 2h over mc. So the change in wavelength is going to be twice the Compton wavelength. So the Compton wavelength is a measure of, you could say it's a measure of how much the wavelength changes if it's a maximum change. That's what it is. It's the maximum possible change in wavelength. The Compton wavelength is the maximum possible change in, not possible change in wavelength, it's the maximum possible, you can see that right there. It's where you get the maximum delta lambda. It's where you get the maximum delta lambda.